and then also on the board. Thank you for the introduction. Okay, so I want to discuss this result I'm going to explain. So first, I'm going to give some definition so that all the notations are set and we're all talking about the same stuff. So first, let's talk about solvable groups and nilpotent group. So fxg a group. Okay, and I can define the derived sequence of G as follows. So define D0 of G to be G, and then dk plus 1 of G is defined as the commutator of dk of G with itself, where this is my notation for so here. So if you have two subgroups A and B, this is the group generated by commutators from elements of A and elements of B. Okay, and this is my notation for the commutator. Brackets. Okay. So this defines a sequence, and we say that sequence of subgroups, and we say that G is solvable if there exists an index E such that the sequence stops. Okay. And we define the derived length of G, so dl of G. This is the derived length, sorry, this is the minimum. The first time the sequence stops. Okay. You can also define the central sequence. Okay. And let me know if I read too small. So the central sequence, you do the same thing, but so define D0 of G, so I put the index on top, so it's an exponent. Is G, and then you define dk plus 1 of G to be the commutator of dk of G with the whole group G. Okay. And G is nilpotent if there exists a time when the sequence stops. Okay, and we define the nilpotency class, nilpotency index, to be the first time where the sequence okay. So of course nilpotent implies solvable. Okay, that's because dk of G is contained in dk of G. Okay. Also gives you a bound the derived length in terms of the nilpotency index. Okay. Well, so maybe a quick example. If J is abelian, then this implies that J is nilpotent, solvable, and actually in that case, the derived length are derived length is equal to the nilpotency index is equal to 1. Okay. I'm going to make one last definition, which is be more group geometric geometric group theory definition, which is the virtual derived length. So what is that? VDL of J. You look at the minimum of the derived length of G0, where G0 is a finite index subgroup of G. Okay, so you look at all the finite index subgroup. So if G is solvable, all the subgroups are going to be solvable as well. And you look at the finite index one, you look at the derived length, and you take the minimum of all of that. Okay, so now I can state the theorem I want to discuss. Take G to be a finitely generated nilpotent group. Okay, and if J acts faithfully on a quasi-projective complex variety X. So what I just mean by that is that G embeds into the group of automorphism of X. Okay, I don't assume anything more on the action. I just want that. Then the dimension of X has to be larger than the virtual derived length of G. So the internal structure of the group gives you constraints on in which dimension you can act faithfully. That's the result. I want to comment a bit on the result and then discuss the tools of the proof, which uses the p-adic method that Serge talked about last week. So as we saw last week, so let me talk about the tools. The main technique is the so-called p-adic method that Serge mentioned last week. And so I want to recall the result of Serge with Juni Xie, which uses the same kind of techniques. And the result they showed is that if you have a SLMZ that embeds into a group of variational transformation of a quasi-projective variety, then the dimension of X has to be larger than m-1, and they even classify the case of equality. Okay, so we saw that last week. So it's a same nature of result. Obviously, this is a bit harder to prove because it's birational, just automorphism. Also, I want to mention actually this result was mentioned in the paper of Serge and Juni. They gave a sketch of proof, but actually there was a bit more complication than what was written down, which was good news for me because then I had more work to do. Okay. So I'm going to talk more about the tools later on. I just want to make a remark, which you might have made to yourself, is that you see in my assumption, I assume that G is nilpotent. But the bound uses the virtual derived length, okay? Not the, you could define like a virtual nilpotency index, right? But this bound, if you replace that by a virtual nilpotency index, it would not work. Actually, let me mention where the idea from that result comes from. It's a theorem of Epstein and Thurston from 1977, which states that if you take G to be a real or complex finite connected finite dimensional Lie group, okay, acting faithfully on a manifold M, then the dimension of M has to be larger than the derived length of the of the group. Okay, and I want also to mention the dual statement on e-algebras because it's actually how they prove it. So on e-algebras you would get that if you have G, which is a finite dimensional nilpotent Lie subalgebra of you look at so I'm going to put omega here. You look at the either smooth or analytic vector fields over your manifold. You take finite dimensional nilpotent algebra, then the dimension of M is larger than the derived length of the Lie algebra. Okay, so same thing here. You have you start. Oh, I forgot nilpotent here. Okay, so same kind of result. You start with a nilpotent Lie group, but the bound you get uses the derived length. Okay, and actually they give a counter example. So they construct a Lie group G such that is nilpotent of index n, well, its derived length is 2, and actually G acts on R2 faithfully. Okay, and actually this is given by polynomial maps. So this also gives you, you can cook an optimal example from my result with this Lie group. Mm-hmm. So yes, so for solvable, so in the case of Lie groups, if you have connected finite dimensional solvable Lie groups, its derived subgroup is nilpotent. So you could apply this result, and you get a bound. That's how usually they also state this result in the paper. As you would see in the proof, you would need some kind of similar statement for p-adic Lie groups. And maybe the result should also transfer to for algebra for solvable. Not clear for me at the moment. No, not that I know of. Yeah. Okay. So, what is the idea of the proof? So there is basically two main steps. So the idea is to use p-adic method. So if I look at my pair X G, so my variety and my group, everything is defined over R, which is a finitely generated ring over Z. I will give precise meaning to that a bit later on, but you can do that because G is finitely generated, so you can look at generators and do that. And your variety is quasi-projective, so it's given by finite number of equations and complements. So you can also do that. So the first step is to use Lesch theorem, which tells you that there are infinitely many ebbening of R into the ring of p-adic integers. This will give you, by base change, a scheme over ZP and an automorphism, a subgroup of the ZP automorphism of this variety. Okay, and up to a finite index, this will give an embedding of my group G into this group of analytic diffeomorphism, of p-adic analytic diffeomorphism. Okay, where D is the dimension of my variety. So this was basically what Serge talked about last week. Okay, I'm going to give some. I'm going to talk about this a bit to remind everybody of what is going on. And then the second step, so what I showed is that actually this group is an infinite dimensional p-adic Lie group. And so if you have a G inside, okay, you can look at the closure of G inside this p-adic Lie group. And what we show is that this is a finite dimensional nilpotent p-adic Lie group. Okay. Then you can look at the Lie algebra, okay, and you can conclude with a p-adic version of Epstein-Thurston's result. Result p-adic version. Okay, so that's the plan of the proof. Okay. So I'm going to talk briefly about this part to do some recall of what we did last week, and then a bit more about this. Let me check the time. Okay, is there any questions so far? Where? Oh, no, it's not C, sorry. So G that was the inclusion. So I assume that I can embed G into the group of analytic diffeomorphism. I showed that this is actually a p-adic Lie group. So you can take the closure of G inside this p-adic Lie group, and G bar, and I showed that it's actually finite dimensional and nilpotent as well. But that was like the kind of step that was missing from Serge and Juni's paper, this part here, to show that the Lie algebra was actually nilpotent as well. Okay. So let me remind quickly, recall what we do with p-adic analysis. Okay, so I fix p prime. Okay. And if I have an integer, I can define its p-adic absolute value by p to the minus p-adic valuation of x. So this is just, you write x as p to the m y with p not dividing y, and m is your p-adic valuation. Okay, and if you have r and q, you can write r as a fraction of integers, and then the absolute value is multiplicative. Okay. The most important thing is that this gives you an ultrametric inequality, which says that the absolute value of a sum of two elements is less than the maximum of the absolute values. So now you have a distance. Which is given by the absolute value of a difference of two elements. This defines the distance over Z, also over Q. And Z and Q are not complete for that distance, so you can take the completion. And this is how you define p-adic integers and p-adic rational numbers. So I'm not giving too much details, but I mean, we saw that last week. Okay, so how do you define? So then QP is the completion of Q with respect to the absolute value. ZP is also the completion of Z with respect to the absolute value. It's also the closure of the integers inside the QP. And as we saw, it's also the ball of center 0 and radius 1 inside QP. Okay, it's the closed one. Okay, and furthermore, and also important, ZP is compact. It's a Cantor set. Okay, so it has a structure of so ZP has a structure of a ring. Also, the p-adic absolute value extends naturally to ZP and to QP because we took the completion. So this is ZP is a ring and QP is actually a field. Actually, QP is a fraction field of ZP. Yes, and one last thing, not one last thing. One thing also I want to mention is that so for all k bigger than 1, you have the quotient from Z to Z mod P to the K. Okay. This extends, this embeds into ZP, and actually this is commutative, so you also have the surjective here. Okay, so this is also ZP over PKZP. And so how do you check that? If you take x, y in ZP, then x is congruent to y modulo P to the K. That is equivalent to say that x minus y is divisible P to the K, so it's P to the K times U, where U is in ZP. Okay? And so this is equivalent to saying that x minus y in absolute value is less than 1 over P to the K, okay? Which is the absolute value of P to the K. Okay. U might be of a lower absolute value or not. Okay. And so you have this description of ZP as a counter set, which is easy to see with this mod P to the K map. So let me just recall this. Is that what is ZP? So this is my ZP. And then I can look at the class modulo P. So I get the class of 0 modulo P. I get the class of 1, 2, and P minus 1. Okay, those are disjoint balls. Okay, this means that you are distance 1 over P of 1, 1 over P of 2, etc. Okay. Okay, and all these points are open and closed actually. So ZP is in fact totally disconnected. I mean, I saw it's a Cantor set. Okay. And then if you were looking modulo P squared or P cubed, you would look at the balls of radius 1 over P to the square or P to the cube. This is what you do. So you also have this description of ZP as the inverse limit of P to the case. That's another description we haven't seen last week. So it tells you that it's basically the same thing as giving yourself a p-adic integers and giving yourself all this residue class modulo P to the K for every K. That's the same thing. Okay. That's clear so far? Of last week? Okay, so now I want to talk about Tate analytic functions. So now we have a complete space over which we can do analysis. Okay, so the first thing you should recall is that if you have a series in ZP, or even in QP, this series converges if and only if the general term tends to 0. Okay, this is because of the ultrametric inequality. And this also makes sometimes p-adic analysis proof easier because estimate on power series is a lot easier to do than for real complex analysis. Okay, so first I want to ask, what is an analytic function? So if you look at the definition over C or R, it's the function which is continuous and locally given by a converging power series. Okay, so this is going to be my definition. Continuous, analytic over. So I'm discussing functions over ZP to the D. Okay. Continuous and locally given by converging power series. But this is not a good class to do analysis with, because the problem you have is that the problem locally constant functions are not constant. Okay? Why? Because you can take the function which is 0 here, and 1 on all these other poles. Okay? Well, this is continuous, right? But it's locally constant, but not constant. Okay, so this class is basically too broad to do anything useful with. That's why one of the reasons you introduce a smaller class, which is a class that Serge talked about last week, which we call Tate analytic maps. Okay. Yeah. Where? No, you're. No, I guess. No, it should be okay with. No, yeah, okay. Yeah, you're right. You don't need continuous. Yeah. Yeah. Yeah, if you're locally given by converged power series, you should be continuous, I guess. Yes. Yes. The thing is, nobody works with that, so I'm not sure what's true or not. But yeah, I think that is okay. It doesn't seem too much to ask. So, okay. So this is why we introduced Tate analytic maps. So I recall space. So ZP of X bar. This is the set of power series. So for me, X bar it's a multivariable. XD. Okay. And when I say X bar to the I, so I is a tuple of integers, and so this is x1, I1, xd, id. Okay? So I look at power series like that, such that the coefficient tends to 0 when I tends to infinity. Okay? Actually, because of this characterization, this is the same as the set of power series with coefficient in ZP converging over ZP to the D. Yes, so that is the main thing, is that this is not a local definition. It's a global one, right? You look at the unit ball, you have natural coordinates on the unit ball, and you want power series in these coordinates that are defined everywhere. Yeah. So I guess yes. But okay, this like when you, because the thing is, if you take any converging power series, if you zoom close enough, it will look like this. It's just it's not complicated to see that because. So imagine this is converging for some radius, let 1/p to the k. Exactly. Because if you just say that, then you can just multiply by p to the k every coordinate. You zoom in on this local disk, you get, or maybe p to the k plus 1. You will get something which of this form, but on a smaller disk, right? So this is not a local definition. I have my ball, my unit ball, and I define state analytic functions on that unit ball with something global. Okay? There's a bit of a subtlety here. But, yes. Also, I want you also want the coefficients to have norm less than 1. This is because you want to compose. Because you can have a coefficient in QP and still have all the image in ZP, or ZP to the D, but then you cannot compose. Okay. Example, because Serge is not. So in dimension 1, this goes from ZP to ZP, because if you look mod P, every integer is congruent, like x to the P is congruent to x modulo P, right? So this is divisible by P. So this has value in ZP, but it has coefficients in QP. Okay, so there's. Okay. Really, you want the constraint on the coefficients and on the radius of the series. Right. Okay, and then the definition is that f from zp to the n to zp to the m is Tate analytic, which I will write TA. If, so you write f as f1 m, and fi belong to my algebra over there. Okay. And so the thing is, with this class of maps, we have the property that I mentioned before. So you have Strassman's theorem that tells you that f from Zp to Zp, which is Tate analytic and not constant, has a finite number of zeros. Okay. And this gives you a corollary, which is that f from Zp to the n, Zp to the m, locally constant implies constant. This also gives you, like, if you have two analytic functions, state analytic functions that coincide on an open set, they have to be equal. So we get a lot more the same theory that we would over C with holomorphic functions, right? So this is a nice class to work with. And so if n is equal to m is equal to d, so the same dimension, then we get a semigroup. So you can compose with composition. Okay, and the Tate analytic diffeomorphism are the invertible elements. Okay. Okay. Right. Okay, then one other thing I forgot to say. So if you have f, which is given by a power series, you can define its Gauss norm to be the maximum of the absolute value of the coefficient. And if you have a Tate analytic function in several variables, you define the norm as the max of the norm, of the Gauss norm, of each coordinate map. And so if f is given by a power series, okay, you can look at f mod p. That is the same power series, but you reduce the zp coefficients modulo p. Okay. And what does that mean? That and you can do that also if you have multiple functions, right? You can reduce each coordinates mod p. And so what does that mean that two functions are congruent modulo p? This is equivalent to saying that the difference of their Gauss norm is less than 1 over p. Okay. So the same discussion we had for the p-adic integers works as well in that setting. Okay. So in particular, I can define this subgroup I can look at diff n 1 of zp to the d, which is the set of diffeomorphism such that f is congruent to the identity modulo p. Okay? Or equivalently, this is the set of diffeomorphism intersected with the ball of center identity and radius 1 over p. And now we can state Bell-Pullen theorem that we saw last week. So this theorem will explain why, for dynamical questions, it's really interesting to look at p-adic analysis and to do this base change to zp. Is that if so you take f from zp to the d to itself, state analytic, and such that f is congruent to the identity modulo p. So I need p to be bigger than 3 here. Then there exists a unique flow from zp times zp to the d to zp to the d, okay, such that phi of 0, so I'm writing my flow phi, and so phi t is my notation for phi of t, and my variable x is for the space. So phi 0 is the identity. Okay, and for all st in zp, phi s plus t is phi s composed with phi t. And the second thing is that the integral time interpolates the iterate. So for all n in Z, phi n is the nth iterate of f. And so in particular, phi minus 1 is the inverse of f. So f belongs to the subgroups of state analytic diffeomorphism that are congruent to the identity modulo P. So this is really strong because interpolating iterates is not something. You could ask that for one orbit you can interpolate the orbit in an analytic curve, but no, here you can interpolate the iterate of the whole map. Okay, and this gives me two immediate corollaries. So the first one we saw last week is that diff n1 of zp to the d is torsion-free. Okay. And the second is that how can I describe diff n1 of zp to the d? Well, this is just identity plus p time a Tate analytic function. Okay. So, you know, you can also, well, I haven't defined properly, but you could look at QP of x bar, right? So, same definition, but you look at power series with coefficients in QP converging over ZP to the D. Okay. Okay, this is actually a Banach algebra, okay? And ZP of x bar is my unit ball in this Banach algebra, okay? So what this tells you actually is that diff n1 of ZP to the D is an open subset of an infinite dimensional Banach space over QP. Okay, so this tells me that this is a p-adic manifold. And looking at the compositions and the formulas, you can show that this is actually an infinite dimensional p-adic Lie group. Okay, so I don't want to go into too much details about that because you have to define what are analytic maps in infinite dimension. In the book of Bourbaki, they do it. And following these definitions, you show that it works for that case. But so the thing is now you can use theory of p-adic Lie groups. That will be kind of useful. Another thing for those who were not here last week, the condition that being congruent to the identity mod P is not that complicated. It's not that hard to get. You can show that if you have a subgroup of analytic diffeomorphism, a finite index one will be inside this. Will be conjugated to a subgroup inside this subgroup. So it's really not that restrictive. I don't have time to show the argument because I want to. Yes, I won't have time to show the argument. Okay, so that's all I wanted to say about the p-adic analysis. All right. Now I want to explain how we do this base change. So I start again with my problem. I have G, which is a finitely generated group. Okay, and it acts on X, which is quasi-projective. Okay. So the thing is, you can embed X into Pn, and then x is given by what? X is given by polynomial homogeneous equations, and you're quasi-projective, so you also have to remove some. So this is a finite set of data, right? So, and then all these elements will have coefficients in a finitely generated ring. So there exists R, finitely generated, a ring over Z, such that what I mean by define over R is that there exists XR over spec R, and let's say gamma R inside the automorphism group of XR, such that X is given by the base change and G is given by the base change. Sorry, not ZP yet, C. Okay, so this is not hard to do. And now you want to go into ZP, so that's the Lesch theorem we saw last week. Let me check. Okay. All right, so Lesch theorem tells me that I have infinitely many embedding of R into ZP. So what I mean is that I have infinitely many prime P, such that I have an embedding of R into ZP. Okay, that's what I mean. Right? And the thing is, you want to ask you would like to ask an as condition for your new models. So you want to you want that when you make the base change, okay. When you make the base change, for example, so this is a scheme over spec ZP. It has two fibers, the generic one and the special one. Okay, and you would like, for example, that both are geometrically reducible, and you would like that you can find a point, a ZP point, such that its reduction modulo P, let's call it alpha, in the special fiber. You want this, and you want alpha to be smooth, for example. You want conditions like that. Why? Because if you take such an alpha, and you look at the local ring at alpha, and you look at its completion, this is going to be actually a ring of power series in D variables. Okay. So that's how the power series come in when you start with your group. Because if you take your group, well, your special fiber has finitely many FP points, so up to finite index, it will fix all of them. So we'll fix this one. And then all your generators will be given by power series, but you can show that actually they're converging and they're elements of their analytic diffeomorphism. Okay. That's how it, because we saw it last week for the affine space. I want to explain a bit more what happens for quasi-projective varieties. Okay, so if you do all of that, you get up to finite index, an embedding of G inside a priori analytic diffeomorphism, but if I take another finite index, I can put 1 here. Okay? Okay, and let me draw it here because I have several embeddings to write. Okay, so this is my first embedding. The other one is you have that G is finitely generated, nilpotent, and torsion-free. So by a theorem of Malchev, I can embed it into the space of upper triangular matrices with one on the diagonal and coefficients in Z. So this space of matrix. Okay, but the star belongs to Z. Okay, so let me call the image gamma. Okay, so, and here I can, okay, I have also the map here. Let's call it also G, the image inside the. Yes, so let's put G0 here. Okay, yes. So G0 embeds into this, okay. But here, I can look at the closure of gamma inside the same space of matrix, but with coefficients in ZP. Okay. This is a finite dimensional p-adically group. Okay. And actually, you can show that this is also the pro-p completion gamma p of gamma. Okay, so the inverse limit of all the finite quotients of size p to the k. Okay. And the thing is, so you want to extend this group homomorphism to gamma bar inside this p-adic Lie group. So to do that, this you can embed into the inverse limit of permutation of zp to the k to the d. Okay, so we saw that actually take analytic diffeomorphism, they permute the balls of a fixed radius, right? So it gives you, for mod p to the k, it gives you a permutation of all the residue classes modulo p to the k. Okay? So you have, this is actually injective, okay? And actually the closure in that is the pro-finite completion of this group. Okay. So what Serge and Juni showed is that actually, if you look at gamma bar here, because it's a pro-p completion of the group gamma, you can extend. It extends naturally to this pro-finite completion here. Okay. So this is not exactly what you want because the image might be larger than what you get. But what they showed actually is that no, the group homomorphism here, it goes into here, and it's actually continuous. Okay? But now you have a continuous group homomorphism between two p-adic Lie groups. It has to be analytic. So gamma bar into, I'm going to write like this. Diff an 1 of zp to the d is analytic. Okay, and the image is exactly the closure of G0 bar inside this group. And so G0 bar is the quotient of gamma bar by the kernel. So it's a finite dimensional nilpotent Lie group. And then one last thing I want to mention is, so you can define G0 to be the Lie algebra of G0, okay? And what you get is that D will be larger than the derived length of G0. So that's Epstein-Thurston p-adic version, okay? This might not be the derived length of G0 because you're in p-adic, so when you have some information on the Lie algebra, it gives you information on the compact subgroup. So this is larger than the virtual derived length of G0. So there's 2 times the finite index appearing, okay? The first one we can control easily. This one is harder to control. And I stop here. Sorry? Yes. No, because so that's no, because you have this counterexample of Epstein-Thurston. You have G acting on R2 by polynomial maps. and the nilpotency of G is n, so any n, but the derived length is 2. Okay, and you act on in dimension 2. This is polynomial, so you can find a finitely generated subgroup in there, such that all the finite index subgroup will have the same properties. So this cannot be made better. Okay, and actually yes. Okay. Wait, can you take the box? I can't hear.
Yeah. So I have the question about the Epstein-Thurston.
Yes.
So the real complex Epstein-Thurston and p-adic Epstein-Thurston, the proof technique is similar or different?
Yes. So the proof. So I don't actually know the proof in the real setting, but in the complex setting, it's easier because and it's the same one for p-adics. The main thing is when you have a Lie algebra of sorry, you look at the Lie algebra of analytic vector field. You can look at the restriction to any open subset, and this is injective in analytic regularity because if you coincide an open subset, you're equal everywhere, right? Okay, so you can look locally, and then the thing is, what you do is you take you can find a vector field X in J, which is which commutes with everybody in your Lie algebra. So then locally, X is just the derivation with the, let's say, with the last coordinate. Okay. What does that mean that everybody commutes with X? It means that everybody can be written with formulas that do not depend on the last coordinate. So then you can just project on the first d-1 coordinate and do an induction in your argument. Same techniques in p-adics, because actually the local how do you call this theorem? Well, you can make everything straight. I forgot the name, but it's sorry. No, but like if you have like m vector fields that commute and they not vanish at a point, you can make them into part of the canonical basis, right? What is the théorème de redressement en français? Anyway, okay. Yes, exactly. And so the implicit function theorem also holds in these p-adic settings, and the proof is even easier because you have to estimate converging power series, and with the ultrametric inequality, it's even easier. So actually, I make that explicit in that paper, actually, because I wanted to make sure everything worked. So yes, so you use that, and that's how the proof goes. In the resetting, I don't know how they do it. I didn't read that's the initial paper. Yeah. Oh, watch out. Oh, okay, not too bad. So do you want to have like a kind of a description of the extremal case like Serge and Johnny did for...
Yeah.
So short answer I would guess is no, because this example is, I don't see why it's very special. Well, I haven't written down the formulas, but what I can say is that the easiest example of nilpotent group you can find is just, but you take the free group, so you take R generators. I mean, you can do it with 2, actually, I think. So you take 2 generators, and but you want to make sure, and you kill all the commutators of length, whatever you want, right? This gives you a nilpotent group of index. Okay. And I studied like when you kill the terms like commutators length 2 and 3, and you can find like action for those. This gives you a kind of extreme case. Yeah, but I think it's quite hard because you don't impose much, right? You want an action on a quasi-projective variety. So I think it's hopeless to try to describe the equality. And you're also up to finite index, so yeah. Yes. Yeah. That is correct. Yes. Yes. So if you yeah. So wait. No, but wait, because you want a nilpotent C large. So. Yeah, you're right. So this goes to ax plus b, and then you. Okay. And then y plus. Yeah. And up to d. Yeah. So up to n. Yeah. So this will be. Yeah. You see that this is nilpotent of class n. But its derived length is 2. Because first commutator kills this part, and then you're just in translation, but 2 translation commute. So. Yes. First one should have written like that. Because in the paper it's quite... Yeah, but that's the example. And well, so, yeah. Also, if you put it in with p-adic coefficients, it gives you also the same bound, but for the p-adic Epstein first one, right? So. Yes, probably. At least, yeah. Locally, yeah. I think locally. I think if your nilpotent and your derived length is 2, you can find an open subset where you're actually conjugated to something like that. That should be a reasonable statement. Sorry, an open subset in the p-adic in ZP to the D. Okay, you can find a polydisk inside ZP to the D where your action is given by that. Yeah, that would be. I think that's okay.